Alright, so today we're going to be working on Chapter 10, Quality Control. Quality control is a process that evaluates output relative to a standard and takes corrective action when output doesn't meet standards. So if results are acceptable, there's really nothing that needs to be done. But if the results are unacceptable, then an organization would take whatever the corrective action is to get those results to be at an acceptable level. So an example of quality control would be a car production. When a car company produces a car, at pretty much every stage of the production of that car, there's some standards that have to be met, and the company inspects those standards, and if those standards aren't being met, either that car is scrapped or it's going to go to whatever part of the production that it's at where it didn't meet that quality. So it's constant with car manufacturers, where they're always trying to check things and to inspect things to make sure that whatever they're producing, it meets or exceeds their expectations or their standards. The best companies design quality in the process. They use it to produce a product or service which reduces the need for inspection. So throughout the production of a service or a product, a company is always designing in quality, so that once it gets to the end result, there's really the inspection is minimal. When companies do inspections alone, as you can see on this phases of quality assurance, that's the least progressive way of doing an inspection, just doing inspections alone. And when they do it, it's not always sufficient to achieve the level of quality. Many companies occupy a middle ground, which is inspection and corrective action during production. So that's the middle ground, and that involves inspecting, and if there's a problem, they correct it right then and there. That way it doesn't move on to the customer. The customer doesn't really see any effect. Now the most aggressive is continuous improvement. Quality built into the process. So these are the three phases of quality assurance. You have inspection, which is least progressive, inspection and corrective action during production, which is the middle ground, and you have continuous improvement. That's the most progressive. Now inspection is when an appraisal activity that compares goods or services to a standard. So these are definitely vital and underappreciated. It's an underappreciated aspect of quality control. So inspections can occur at 3 different points: before production, during production, and after production. During or before production, that's done to ensure that the inputs are acceptable. So anything that's going into producing a product or a service, they want to make sure that whatever that input is acceptable. During production, that's to make sure that the conversion from whatever was going into the production of the product, that the output is performing at an acceptable level. Production inspections performed after production, that's kind of a confirmation that the outputs meet whatever acceptable level an organization sets before they pass it along to the customer. Because once it gets to the customer and it's not up to the level of quality that customer expects, either that customer is going to return the product they're going to keep the product but never want to do business with that company again, and they're going to also possibly give it bad reviews or bad feedback. So the best way to make sure that a product or service is of quality is to do it before it gets to the customer. So one question that needs to be answered is, how much and how often should an inspection occur? And this chart, this figure here, kind of goes over what the total cost is of an inspection. The little orange line, that's the cost of passing defects on to a customer. So as you see, if you do little inspection, the x-axis is the amount of inspections, the y-axis is the cost of it. So as you do little inspection, the cost is up here, little inspection, so it's gonna, that cost is gonna be passed on to the customer. It's gonna be a higher cost. This blue line is the cost that the company incurs to inspect. So the amount of inspections that you do, the cost just gradually increases. And the little dash line here shows the total cost, which is the sum of the cost of the inspection plus the cost of passing the defects on to the customer. This little dotted line in the middle, the optimal level, is where the cost of inspection and the cost of passing the defects on to the customer, that's where they intersect. So as you can see, again, on this chart or on this figure, the cost ranges, depending on who you want to take on the cost, that's the number of inspections you want to do. So things like low cost, high volume items like paper clips, nails, pencils, those aren't inspected as much. So that cost is usually passed on to the customer because they're low cost but they're high volume, so they're pumping out a lot of items. Now the things that do require a lot of inspection are high cost, low volume items like airplanes, vehicles, cars, trucks, spaceships. Those get a lot of inspection because if you pass on some defective parts to a customer, as far as like airplanes or any type of automobile, if that defective part gets passed on to the customer, well, that cost of repairing it is a lot higher because you got safety, you have people's lives that could be lost because you decided not to do as much inspection. So again, you want to answer the question of how much inspecting you want to do of a product or service and how often you want to do that inspection. Many operations have numerous possible inspection points, and because each inspection adds to the cost of the product or service, it's important to conduct inspections to the points where it's the greatest value is being added. So another question to answer is where to inspect in the process. I'll give you an example of how the utility company that I work for, how we inspect software when we do a software upgrade. Every year or so we have to upgrade our energy management system software, and like every 3 or 4 years we have to upgrade the hardware with the software. Every year that we upgrade the software or patch it, we have to do a lot of checking of functions, the functionality of the software. So the initial thing is we put them on our development servers where we're inspecting, we're making sure that if we click this button or if we input this value, this will happen. After about 3 to 6 months of testing in our development system, then we upgrade the software on. If we're upgrading software and hardware, we put the software on our new hardware, and we run pretty much the same tests to make sure that the software is functioning. So we're inspecting in a development environment and then a pre-production environment with new hardware, new software. And that usually takes between 2 to 3 months of testing to make sure, again, the functionality of the software and the hardware. We want to make sure that if the hardware or the software fails over or fails on one server, because we have 3 servers for the energy management system, so we want to make sure that if the software or the hardware fails on the primary server or system, it's going to fail over to the next one. So we're checking functionality for that. We're checking functionality that if we push a button to open up a breaker, that breaker opens. If we push a button to close the breaker, we want to make sure it closes and it stay closes. So we're always inspecting it. We're inspecting in development, we inspect it in pre-production, and then also when we do our cutovers, when we upgrade the system and the software and the hardware, we make sure that, like, we do one server, one system at a time. So we'll do server A, make sure it's functioning for the operators and dispatchers. Then we'll move on to server B. So once we move to server B and make sure it's operating and functioning properly, we'll have a redundant system. We'll have 2 servers up, and we're going to make sure that server A can fail over to server B. If something happens to server A, we want to make sure it automatically fails over to server B. After we do that, we get to a point of no return, or what we call a point of no return, which is before an irreversible process happens. Because once we cut over, or once we upgrade that 3rd server, it's going to be very difficult to move back to the old system or the old hardware. So we want to make sure that once the C server's up, right before we bring the C server in, that everything is functioning properly. We make sure that the operators are on the call, the dispatchers are on the call, and that they have confirmed and tested everything that they needed to test before we get to that irreversible process. Once we move over to the server C and upgrade that, we have 3 servers running, so that if server A is the primary, we have 2 standbys behind it. If server A fails, it fails over to server B. If server B and A fail, we have server C ready to go. So you always, when we inspect our software or hardware, when it's time to upgrade, we do it at each step, each level. So we do it at the development level, the pre-production level, and also at the production level, because we want to make sure that everything is functioning as like it's supposed to. Because if we click a button once that new system's up, if we click a button to close a breaker and it doesn't close, that could jeopardize someone's life. So we want to make sure that everything is tested and inspected to work properly. Alright, so when inspections are performed, companies have to decide whether to perform the inspections off-site or centralized versus on-site. And this depends on the effect on the cost and the level of disruption for the production of that product or service. You use off-site or centralized when inspections when the tests are specialized, because it may be best to complete in a lab. So things like medical testing, that's usually done off-site. When food's analyzed, that's usually done off-site from wherever the food's being produced. So anytime there's specialized testing that needs to happen, the inspection's usually done off-site. You would use on-site inspection when quicker decisions are needed. So when a car manufacturer, If they need to inspect a steering wheel, it's usually not sent to a lab or anywhere. It's inspected on site because you need to decide whether or not to fix the steering wheel or just scrap the whole vehicle and start all over. So steps in controlling, having an effective control process. The first step is to sufficiently define what's to be controlled. It's not enough, for example, to simply refer to a painted surface. For example, the paint has a number of important characteristics, like how thick it is or the resistance to fading or chipping. So there's different characteristics that go into just something as simple as paint, that requires different approaches to controlling the process or the inspection. It's also important to consider how measurements will be accomplished. Are you going to use only characteristics? You want to use only characteristics that can be counted. The next, you have to make a standard of comparison, so that you can measure something and evaluate it based off of whatever it's being compared to or something that it's compared to. Next step is to establish a definition of what's out of control. So every process that's functioning, if it's functioning as it should, it shouldn't yield output that conforms exactly to a standard. So even if it's performing as it should, it might not be exactly in that standard, even though it's functioning like it should. So the main task of doing quality control is to distinguish between random output versus a non-random output. So some things that could cause non-random output could be things like worn equipment, incorrect methods being used when producing something, and failure to follow instructions. So if you find something that's non-random, you want to fix that problem. And then the last step is to monitor the fix, whatever you fix, to ensure that whatever you fixed and how you fix it is effective. So the output of a process, you have to monitor it for a sufficient amount of time to verify that the problem has been eliminated. So you have to monitor it. An important tool in statistical process control is what we call the control chart, which was developed by Walter Schuhart. The control chart is a time-ordered plot of samples obtained from an ongoing process that are used to distinguish between random and non-random output. It has an upper control limit. So when it's above this line, that means that it's out of control. And it also has a lower control limit. So anything outside these two lines, the upper control and lower control, that means that it's out of what we expect. Alright, so it's important to recognize that because any limits can end up on the tail end, so lower control limit on one end, upper control limit on the other end, that the distribution will fall outside of the limits even though only random variations are present. So we have things called the type 1 error and type 2 error. The type 1 error refer to the probability that an item is rejected when it may appear that the process is out of control. It's not in control, so it's out of control when it actually is in control. Now this is what we call it's a manufacturer's risk. Type 2 is the opposite. Type 2 errors, that's when the process appears to be in control when it's out of control. So that's a consumer risk. So type 1 is when a manufacturer may think something's wrong, but it's not. But type 2, which is very costly, is when a manufacturer gives a product or a service to the customer, and it might look like it's okay, but it's not really okay. So again, you have your lower control limits on this end, and you have your alpha risk, which is the sum of the probability of both ends. So alpha refers to LCL, lower control limit, plus UCL, upper control limit. There are 4 commonly used control charts. 2 are used for variables or data that is measured, and the other 2 are used for attributes or data generated by counting. The 2 types of control charts, which we'll go into a little bit more in depth, 2 types of control charts used for variables are, one, the mean control chart, which we'll do a couple of examples on that, and then the other one is the range control charts. A mean control chart, or what's referred to as the X-bar chart, is based on normal distribution. It can be constructed in 2 different ways, which, depending on the information, you'll decide which way to construct it. The range control chart, or what is referred to as the R chart, that's used to monitor the process, and it's sensitive to any change that might occur throughout the production. We're going to work through an example and come up with control limits. We're going to come up with the upper control limit by using this equation, and we're going to come up with the lower control limit by using this equation. And we're going to use a chart to get this A2. We're going to use factors for 3 sigma control charts, and 3 sigma refers to data within 3 standard deviations from whatever the average is. So we're going to use this chart on 10-25, table 10.3. You're going to use that. We're going to use that for this example. You're going to need to use it for your homework, and you're also going to need to use it for the quiz that you'll have. So just make a note of this chart on 10-25. Alright, so for this example, create a control limit chart using the observations and samples below. So the first thing, I highlighted everything, the different steps that you need to do to come up with the control limit chart. So the first thing you have to do is find what the mean is, the grand mean. And that's by you take an average of each sample and you average out those averages. We did the average for sample 1. Excel does a good thing when you highlight all of the numbers. So the average of that is 12.1 or 12.10, however you want to do it. But if you want to do it the old school way or the right way so that you learn it, you do 12.1 plus, or 12.11 plus 12.1 plus 12.11 plus 12.08 equals, and then you divide that by 4 observations, and that's where that 12.1 number comes from. After you get all of the averages of each sample, then you need to add these up and get the average of that, and it looks like it's 12.11 based off of what Microsoft Excel is telling me. So we have our grand mean, which is equal to 12.11. The next step is to find the average range. So to do that, you take the largest and the smallest observation of each sample. So for sample 1, I would take 12.11 and subtract it by 12.08, which would give me 0.03. So I'm gonna, let me find out what that color is and make it that color. Okay, so I'm gonna put average range equals, I need to make that green, not the same green, yeah. So it would be 0.03 for sample 1 plus the range from 2 through 5. So after we get the range for all 5 samples, which we have 0.03 plus 0.05 plus 0.06 plus 0.04 plus 0.05. Put that plus in there. Then whatever number we come up with, then we divide that by 2. So 0.03 plus 0.05 plus 0.06 plus 0.04 plus 0.05 equals, we divide that by 2, 0.115. So that would be our average range. So instead of dividing it by 2, you're actually supposed to divide it by 5 because you have 5 samples. And that number is 0.046. The third thing, after we have come up with the grand mean and we have the average range, the next thing we need to do is use table 10.3, which is on slide 10-25 and on page, and it's also on page 433 in the book, to come up with the control chart factor, or the A2. So we have 4 observations, so we're going to go down to 4 on the chart, and that's going to give us 0.73. So that equals 0.73. And after we get that, we can come up with our control limits. So let me insert a couple of fields. So our upper control limit, change the color, something different. So our UCL, or upper control limit, is equal to 12.11, which is our grand average, plus 0.73 times our average range, which is 0.046. Alright, so that gives us our upper control limit is 12.14. Our lower control limit, I need to change that color. Our LCL, or lower control limit, is, the equation's similar, but instead of adding, you subtract whatever the 3 sigma control chart tells you the value is. 0.73 times 0.046, and that equals, alright, so the low control limit is going to be 12.08. We'll save that. Alright, so after you come up with those, you can come up with your chart. Now, I used Excel. You can draw it, but I use Excel for it, and we can just highlight that charts. I don't like that. Let's go to more, all, and select scattered. So this kind of gives you an ideal. So remember, our control limit, our upper control limit is 12.14, which is this, and our lower control limit is 12.8. So if you think about it, we have 2 points that are out of the control limit, that's in the upper control limit, and we have 2 points that's right on the lower control limit. So that's how you're expected to do it for your homework assignment and the quiz that you're going to have next week. Let's insert, see if we can insert the line. So make that black and make it a little wide. So that's your upper control limit, and your lower control limit, we'll put it just below 8 so you can see those two. So anything inside of the upper control limit and lower control limit, that's acceptable and expected. Alright, so the next thing we can do with the information that we got from the control limits is come up with control limits, but it's from the control chart. So we'll come up with the control limits, and the equation for that upper control limit is equal to D3, or is it D? It's D4 times our average range. So D4 refers to the upper control limit that's listed in table 10.3. So again, we have we're using four observations. So this would be, upper control limit would be equal to whatever the D4 value is, or the upper control limit on the control table, and control table 10.3, which is 2.28, and we multiply that by our average range, which I think was there it is, 0.046. So we multiply that times 0.046, and that equals so based off of the average range and the factors for the R chart in table 10.3, we have 0.105 minutes, and we have 0 minutes as the lower control limit and the upper control limit. You will have to know that for your quiz. Okay, the control charts for attributes, again, there's two charts. We have the P chart and the C chart. You would use the P chart when observations can be placed into two different categories. So examples of that would be good or bad, pass or fail, does it operate or does it not operate. You would use the C chart only when the number of occurrences per unit of measurement can be counted. So examples of that would be, if you were looking at a car that was being produced, are there any scratches, any chips, any dents, any cracks, any breaks, anything broken, anything torn? So that's when you would use the C chart. So using control charts adds to the cost and the time needed to obtain whatever output an organization is trying to do. The best organizations strive to reach the level where the process and the quality of what they're producing is high. This is why the organizations might use control charts at various points of whatever process they're going through. In the organization, the managers, they have to make a number of important decisions about when and how the control charts will be used. So managers have to consider what sample size is going to be taken. Sample size is very important for two reasons. The first reason is because cost and time are functions of the sample. So the bigger the sample size, the bigger the cost of inspecting that sample size is going to be. The other reason is that smaller sample sizes are more likely to reveal some type of change in a process than what a larger sample size would show or reveal, because a change is more likely, it'll more likely take place within the large sample than between small samples. In some instances, managers can choose between using a control chart for variables, or which is also the mean chart, or they can use it for attributes, which is the P chart. You use the mean chart for things like when a manager wants to monitor the diameter of a specific part, if it's, if you're putting some type of product together. Either the diameter can be measured, and a mean chart can be used to control, the output of that part. Or if the part could be inspected using a go, no go, good or not good, which would indicate whether the part is within whatever specifications that organization sets, without giving it an exact dimension. For this, you can use the P chart because you're just trying to base it off of attributes and not actual numbers or factors. So quality is a major consideration for pretty much all customers. So achieving and maintaining quality standards is very important for an organization. Quality assurance and for products and service design are two important links and processes for the organization, and the organization should continue to seek to increase the capability of the processes that they do when they're putting together a product design or a service design, so that they can move from a position of using inspections to one where quality is built into that product or service design. Okay, for your quiz, the key terms you want to know: control chart, control limits, inspection, mean control chart, quality control, random variation, run test, and specifications. The problem that you'll see on your quiz would be similar to problem number 2, and that's on page 451. So you'll see something like this for your quiz as well as on your homework. The questions that you need to be able to answer, or the question, would be question number 5.